As a space researcher, I spend my days staring up at the stars, and honestly, I am constantly mind blown by the sheer scale and strangeness of our universe. Every time we build a better telescope or run a more complex simulation, we don't just find answers, we uncover completely new reality bending questions. So let's dive into this explainer. Today, I'm opening up my personal casebook to share the top 10 unsolved mysteries of the deep cosmos. These are the phenomena that literally keep astrophysicists awake at night and completely defy our current understanding of physics. In this explainer, we're going to cover 6 main areas: the 95% problem, breaking laws of physics, cosmic flashes and solar mysteries, the pull and the silence, a quick pop quiz to test your memory, and finally, changing our future understanding. Let's get right into it. Section 1, the 95% problem. To set the baseline for our cosmic investigation, we've got to start with literally the most humbling fact in all of modern science. It's something that completely reframes everything we think we know about reality. Think about everything you've ever interacted with. Every star, every planet, every human being, and your morning cup of coffee. All of that normal matter makes up just 5% of the universe. That means a staggering 95% of reality is completely missing from our direct perception, dwarfed by the massive, invisible unknown of dark matter and dark energy. It's kind of like walking into a massive mansion, but you're only allowed to see and interact with the front porch. That is exactly where astrophysics is right now. So what's in the dark? Well, first up is dark matter, making up about 27% of everything. It's completely invisible. It doesn't emit, absorb, or reflect light. We can't see it with any telescope. So how do we even know it's there? Gravity. When we look at spinning galaxies, they're rotating so incredibly fast that the gravity from their visible stars isn't nearly enough to hold them together. They should just tear themselves apart and fling stars out into the void. But they don't. Dark matter acts like this invisible scaffolding. It's an unseen, immense gravitational glue holding the whole shebang together. And on the flip side of that coin, we have dark energy, which makes up a whopping 68% of our universe. While dark matter pulls things together, dark energy forcefully pushes the universe apart. It acts as a sort of repulsive gravity. A great way to visualize this is to picture baking a loaf of raisin bread. The dough is the fabric of space, and the raisins are the galaxies. Dark energy is like the yeast, expanding the dough in the oven. As it expands, every raisin pushes further away from every other raisin. Figuring out what this actually is, that's arguably the single biggest outstanding problem in all of modern physics today. Section 2, breaking laws of physics. Let's move deeper into the mysteries, because out there, in the dark, there are extreme cosmic phenomena that don't just stretch our understanding, they completely shatter the laws of physics as we know them. Take the black hole information paradox, for example. Black holes have gravity so intense that not even light can escape. But here's the problem. We have 2 highly successful rulebooks for the universe that absolutely hate each other here. Quantum mechanics tells us that information can never be fundamentally destroyed. But Einstein's general relativity suggests that anything falling past a black hole's event horizon is gone forever. So if you toss a book into a black hole, is the information deleted or is it preserved somehow? Our 2 greatest scientific theories are locked in a cage match here, and neither is backing down. Drilling even deeper, we hit the singularity, the exact center of a black hole. This is an infinitely dense point where all that mass is crushed down into essentially zero volume. So what actually happens there? Honestly, we are completely in the dark. At the singularity, our math just throws its hands up and quits. The equations start outputting infinities, which is basically a mathematician's way of saying, I have absolutely no idea. And jumping from the incredibly small to the incredibly large, we encounter the Hubble tension. This is a massive puzzle about how fast the universe is expanding. Imagine 2 people measuring the exact same room with 2 different tape measures. One team measures the cosmic microwave background from the early universe, and the other measures local exploding supernovae. They're looking at the exact same universe, but they keep getting totally different expansion rates. It's wild, and it tells us we are definitely missing a massive, fundamental piece of the standard cosmological model. Section 3, cosmic flashes and solar mysteries. If structural and mathematical anomalies weren't enough to make your head spin, we've also got some crazy energetic events firing off across the void. Let's start right in our own neighborhood with the sun. The sun's visible surface sits at a toasty 6,000 degrees Celsius. But as you move outward, away from the surface into its outer atmosphere, the corona, the temperature suddenly spikes to between 1 and 3 million degrees. That is literally like stepping backward, away from a roaring campfire, and somehow the air around you gets millions of degrees hotter. There is some unknown mechanism, probably complex magnetic waves, pumping massive amounts of heat into the corona, but exactly how it works is still a massive mystery. Looking further out into deep space, we find some terrifyingly powerful energy engines. We detect these flashes called fast radio bursts, or FRBs. They last just a millisecond, but in that fraction of a second, they release as much energy as our sun produces in decades. We think they might be linked to magnetars, which are incredibly dense, highly magnetized dead stars. Alongside FRBs, we've got ultra-high-energy cosmic rays, protons traveling near the speed of light. They pack millions of times more energy than anything we can generate in particle accelerators here on Earth. Something out there is firing these cosmic bullets, and we don't know what it is. Section 4, the pull and the silence. Bringing our focus a bit closer to home again, we find some deeply unsettling gravitational pulls and a very eerie cosmic silence. We have this phenomenon known as the Great Attractor. Our entire Milky Way, along with neighboring galaxies, is being pulled through space at millions of miles per hour toward a spot about 150 to 250 million light years away. But the crazy part? We can't even see what's pulling us. It's hiding behind the thick dust of our own galaxy in an area astronomers literally call the zone of avoidance. It's like sitting in a car being pulled by a giant invisible magnet hidden in the fog. It's likely a massive supercluster of galaxies, but it remains hidden in the shadows. Space also loves to throw us local curveballs. Take Oumuamua, our solar system's very first known interstellar visitor. It had this strange cigar-like shape, and as it left, it mysteriously accelerated in a way we couldn't fully explain with typical comet behavior. Then there's Tabby's star, which randomly drops its brightness by up to 20%. For a star to dim that much, something massive has to be blocking it. Theories range from giant clouds of dust to disrupted comets to, yes, even alien megastructures like Dyson spheres. And speaking of aliens, that brings us perfectly to the Fermi paradox. The observable universe has roughly 2 trillion galaxies and septillions of stars. Statistically, the probability of intelligent life evolving somewhere out there is incredibly high. Yet, nothing. Zero contact, no signals, no definitive evidence. This stark contradiction between the high probability of life and the absolute lack of contact is the Fermi paradox. Where is everybody? The silence is honestly deafening. Section 5. Pop quiz. Test your memory. All right, we've covered a massive amount of cosmic territory, so it's time for that pop quiz I promised earlier to see how much of this explainer you've actually retained. Here's your question. What mysterious substance acts as the universe's invisible scaffolding? Think back to our very first mystery. It's the stuff that keeps spinning galaxies from flying apart, and it accounts for roughly 27% of everything we know. Got your answer? The answer is dark matter. If you got that right, awesome job. You are perfectly tuned in to the unseen forces shaping our universe. Section 6, changing our future understanding. Let's wrap up by looking at the big picture and why solving these case files actually matters for all of us. You know, investigating these enigmas isn't just space trivia. Unlocking the mechanisms behind dark energy or figuring out the physics of a black hole singularity is going to completely rewrite our foundational understanding of reality and physics. Just like discovering quantum mechanics gave us the modern computing age, conquering that missing 95% of the universe will inevitably unlock technologies and paradigms we literally can't even dream of today. So I want to leave you with this final provocative thought. If we're currently blind to 95% of our universe, what other fundamental laws of physics are waiting out there in the dark, ready to completely rewrite humanity's future? The universe is vast, bizarre, and incredibly beautiful. Keep looking up, stay curious, because the biggest, most world-changing discoveries in human history are still hiding out there in the dark, just waiting to be found.